Okay, here we have Statistics, Chapter 4, Probability, another fantabulous resource made by the one and only Dr. Frost. Okay, let's get started. So this has been modified to follow the international A-level, okay, stats that's different to the UK one. Okay, so what we are going to be looking at is basic probability, which is an extension which is similar to GCSE. Venn diagrams, again, we've done this in GCSE. Mutually exclusive and independent events. We have done a little bit in GCSE, but we're going to extend on this. Tree diagrams, we have done a lot of this in GCSE. Now, it says changes since the old syllabus. Now, don't read what this says, listen to what I say. Conditional probability and the addition rule are in S1 for international A-level. In the non-international one, they've moved it to year 2. And then it says there's no longer use of these set notations. We will use this set notation, okay? I've combined all the PDF. Don't panic. So basically, we're doing everything on this page. Okay, so here we go. So, what we have here is an experiment. We love experiments, okay? And with experiments, it's a repeatable process that gives a number of outcomes. So an event is a set of one or more of these outcomes, and a sample space is the set of the possible outcomes. For example, here is a sample space diagram. This sample space diagram is because two first spinners each have 4 sectors numbered 1 to 4. They're spun and then the sum of them. So you can see here, all the options for spinner 1, 1, 2, 3, 4. The options for spinner 2, 1, 2, 3, 4. And then what have we done? We've added them. These numbers here are the only outcomes available. Anything else is impossible. Now, this says, what is the probability of obtaining a 5? It's really simple. In your list of outcomes, how many 5s can you get? It's 4 out of a possible 16, because this is the total amount of outcomes. Now, 4 over 16, we can simplify to a quarter. Now, this probability says, what is the probability of a number being greater than 5? This does not say greater than or equal to 5. We're not including 5, okay? Greater than 5, there is a total of 5, 6 out of 16. 1, 2, 3, 4, 5, 6. Again, we can simplify this. 3 out of 8. Now, I don't tend to simplify when I'm working in probability, because we all know that when we're working with a certain thing, probabilities have to add up to 1 essentially, don't they? I tend not to simplify, and that's okay if you don't, as long as you know how to, which we all do. So then, here we go. Straightforward GCSE question. What's the probability of getting less than or equal to 9? Okay. We have the time in minutes here. Less than or equal to 9 is, what is the total frequency? Because this is what it's going to be out of. The total frequency is 6 plus 13 plus 12 plus 5 plus 4. 40. And what is the total frequency of getting less than 9 or equal to? So actually, less than or equal to 9 is 13 plus 6. Which equals, well, this is wrong then, isn't it? Because this is, what we're working out now is less than 9. Let's change this sign for this question. Okay, let's just change the question to, there we go. Less than 9, this is definitely correct. This is going to give me 19 over 40. Now, if it was less than or equal to 9, you're going to see what we're going to do. What we're actually going to do now, as you can see here, we want the probability of having greater than or equal to 10.5. 10.5 is roughly in this interval somewhere, isn't it? Okay, we're going to do our favourite thing, interpolation. Okay, now the thing with interpolation here is we're going to assume that it's evenly spread out. okay? So when we're doing probability, we're going to assume a bit more of an even distribution. So for example, 9 to 11, okay? Where is 10.5 in terms of that? If you think between 9 to 11, so this is 9 to 11. 10 is here. 10.5 is going to be here, isn't it? So it's 3/4. Absolutely, 3/4. So, this doesn't match my actual. It's 3/4. But actually, because we want greater than or equal to, we just want a quarter. So if we just want a quarter, because we just want the 10.5 to 11 part, don't we? We want that, we want, and all of this. What would the frequency be then? What is a quarter of 12? 3. So this is going to be 3. So we're going to have 3 plus 5 plus 4, because we want greater than 10.5, all over our total, which is in fact 40. 3 plus 5 plus 4, 12 over 40. Here we have Venn diagrams. Now, they allow us to combine events, okay, of when two events happen. So the event of A and B, remember, we would write this as A intersection B. And the intersection is where they cross. A or B is the union. They've got married. So we want the whole thing, don't we? Okay? Not A. Everything not A. A dash. Okay? And A and not B, this is A union B dash. Because this is A, we have A with the union of not B. Is that right? I think this is supposed to be intersection. A intersection not B. Okay? Not union, sorry everyone. A intersection not B. Okay then, so when we have these frequencies, we can put them into probability diagrams. So what is easy to do is to draw a probability diagram and think about what's going on. So, first of all, we have the probability of A is 0.6 and the probability of B. So you know when you're drawing this Venn diagram, how many circles you're going to have? 2. One represents A, one represents B. Now remember as well, we've got the universal set on the outside. Okay. Now it says, given the probability of A is 0.6, this means this whole area equals 0.6. Because it's the probability of A, and A is this circle. It then says the probability of A or B. Now, A or B means the union. Now, the union, so the probability of A or B is the probability of A union B, which we know, if we're looking for the probability of the union of A and B, A or B, we're looking for this whole thing, aren't we? So we're saying this whole thing, okay, is 0.85. So from that information, what can you tell me? What can I definitely deduce? I can deduce that this side of B is 0.25. because I know that A is 0.6, A or B is 0.85. Now we also know the probability of A union B is 0.85. So actually we are able to figure out what the probability of the universal set on the outside, neither A or B, is going to be a whole one, take away 0.85, which is 0.15. Because remember the probabilities within this Venn diagram, all of them need to add up to 1. Okay? So, it says here, find the probability of not A, so this is the probability of A dash, and, which means intersection of B, the first question. And then part B wants the probability of not A or, which is union, not B. Okay? So, I mean, we've already started filling in this diagram. Now, it hasn't really told us any more information. So, really, if we're not sure, we can just put this is 0.6 because we don't know any more information here. We can't fill in any more. But we know the whole of A is 0.6. We're not sure what the intersection is here. Okay, so this one says A dash. Now, whenever I work with Venn diagrams, I have to visualise what's going on. And I'll draw a quick sketch, okay? Where is not A? And I use 2 colours. Not A is here on the outside, and not A is this part here, isn't it? Okay, so my not A is essentially in red. Then I do the next part. I don't worry about if it's intersectional union. Where is B? B is this part and this part. Now it clearly says intersection. Intersect. Think about, what does the word mean, intersect? Yeah, where they overlap. Okay, which area do they overlap? Turns out they overlap in this section here, not the whole of B, but just this part of B. This is where they overlap. So therefore, our answer is 0.25. Okay, we've got that from the Venn diagram. Now here, again, if I was to do this, I would draw this out. So step 1, quickly draw a Venn diagram. Okay, we will get better at this, and there are some rules that we are going to learn further on. Now, again, my A is always going to, so A dash, red. Red, not A is this part, and not A is this part. Okay? My B dash, not B, I'm going to do it in green. Where is not B? This is not B, and the outside is not B. Now it says the union. It can't be right. Yeah, sorry everyone. I accidentally put it's not the union here. It's neither A. It's neither A and B. Okay, so it is intersection again. So where is the intersection? It's the outside, which we know is 0.15. Okay, give this one a go on your own. Start by, you should all be happy creating Venn diagrams, and then let's have a look at the probabilities. Okay, so what we should have is whenever you read these types of questions, I always aim straight for the overlaps. So 25 own dogs, so I can, if I want, I could just put 25 here. So I know that this whole circle's got to be 25. 15 own dogs and cats. So dogs and cats, I know this whole area's got to be 15. Hopefully I'll find some that own a few different things in a minute. Here, 7 own dogs, cats and tropical fish. Right, I found that middle overlap. It's going to make my life so much easier. Now, I know there's 15 own cats and dogs, but 7 own free, so 50, take away 7 is 8. Okay, and then what I'm also going to do is underline what I've done. 11 own dogs and tropical fish. It's 40 fish in total. Dogs and tropical fish is 11. We've already got 7, so that's 4. 53 own cats. I'll just put that there. 10 own cats and tropical fish. So that's going to be 10 take away 7 is 3. 40 own tropical fish. Okay, so now I'll be able to figure out 8 plus 7 is 15 plus 4 is 19. So that means 6 dogs in total will give me 25. Okay, then we're going to have 18 plus what is 53? 35. And then, so that makes 53. Then I'm going to have 14 plus what is 40? 26. Now I am going to add them all up because it says 100 of her clients. Now, if it doesn't equal 100, that just means that some of her clients, yeah, they could have a bird. But let's add it up. Let's see what it equals. It equals 89. So that must mean 11 do not have a cat, a dog, or a fish. Okay, they could have birds, horses, tarantulas. So then, part A says the probability that they own dogs only. So that is just this part here, which is 6 out of how many altogether? 100. 6 over 100. Part B, does not own tropical fish. Okay, so where does not own tropical fish? 6, 8, 35, 11, which is 60 over 100. And then lastly, does not own dogs, cats, or tropical fish? Well, it's 11 over 100. Fantastic, nice and easy. Okay, so what I want you to do is test your understanding with this question. Now, bonus points available. If you can get this part of the question, which is worth 3 marks, you get bonus points. Why? Because this is called conditional probability. Let's see if you can understand why. So, start by drawing a Venn diagram and filling in the one that says do all 3, and then from there you'll be able to work it out. Here's one I did earlier. So, as we can see, here are the answers. Okay, and, so we've got the answer to A, B, C, D. Now, the answer for part D isn't in there because we're going to do this together. Okay, so we should have filled in our Venn diagram, and for the first one, it's none of them, it's the number on the outside, 7 out of 100. For part C, swims but does not run. So they're a swimmer, but they don't run. Okay, that needs to be 3 plus 8. It's not just 3. Okay? Because where do they swim and not run is this whole section here. And then the last one, it says takes at least 2 types of these exercises. So we are going to have to add up, 15 take at least 2, 25 take at least 2, 10 people take at least 2, and 5 take at least 2, which is going to give us 55 over 100. Okay? Okay, then the last one says, Jason is one of the members from the above group. Given that Jason runs, find the probability that he swims but does not cycle. I'm going to give you another minute to have a conversation. Really think about this and actually take an educated guess of a probability. Off you go. So, the key is in the sentence. Given that Jason runs, okay? Given that he is a runner means given that he is one of these people right here. How many of these people are there in total? 65. So our probability is going to be out of 65 because this is given that Jason is a runner. He's done the couch to 5k, hasn't he? So it then says, find the probability that he swims but does not cycle. Well, if we looked at this one, this is the probability that he cycles and does not swim. This is the probability that he cycles and swims. This is the probability that he just swims. So the answer is 15 out of 65. Mutually exclusive events. So if two events are mutually exclusive, what do you know? Really think about this. What does the word exclusive mean? So if you have two mutually exclusive events, I mean these two events can have nothing in common. Okay, they can't happen at the same time. So if A and B are mutually exclusive, the probability of A and B, this means the probability of A intersection B equals 0. Okay? The probability of A or B, so the probability of A union B would equal the probability of A plus the probability of B. These are rules you need to know. How would the Venn diagram look if two events are mutually exclusive? They would look like this. A, B, universal set. Two events are independent. If two events are independent, then whether one event happens does not affect the probability of the other happening. Okay, so if A and B are independent, then this is the same as the probability of A intersection B equals the probability of A multiplied by the probability of B. Another rule you need to know. Here's some examples. I pick one of the four numbers, 1, 2, 3, 4 at random. What's the probability that I pick a multiple of 2? Well, there's two multiples of 2 out of a total of 4. So it's 2 out of 4. I pick a multiple of 4. 1 out of 4. So we're going to explain conceptually why these two events are not independent. So these two events are not independent because if it is a multiple of 2, then it must be, if it is a multiple of 4, then it must be a multiple of 2. Yeah? So, but if it wasn't a multiple of 4, then it may or may not be a multiple of 2. So the events are linked, and whether one happened influences the probability of the other happening. So, for example, the probability of a multiple of 2, I'm going to put M2, is everyone happy with that? Times the probability of a multiple of 4. This is 2 over 4 times 1 over 4, which is 2 over 60. We could simplify this to 1 over 8, okay? Now, if they are not independent, therefore, this is not going to be the same as the probability of a multiple of 2 and a multiple of 4. What does that equal? So if I was to draw this as a Venn diagram, okay, multiple of 2's here, multiple of 4 here. Let's think about it. Multiple of 2's is 2, and then a multiple of 2 and 4 is 4, yeah? Multiple, 1 would be on the outside and 3 would be on the outside. Everyone happy? So a multiple of 2 and a multiple of 4, we know is just 1 out of 4. So we've shown that these events are not independent because we know that A intersection B, if they are independent, the probability of A intersection B will equal the probability of A and B. Does 2 over 16 equal 1 over 4? Does not equal 1 over 4. Therefore, not independent. And this is because the probability of A intersection B does not equal the probability of A multiplied by the probability of B. So then, we have a few more examples to look at. Events A and B are mutually exclusive. Probability of A equals 0.2 and the probability of B equals 0.4. So the probability of A or B, we know this is the probability of A union B. And what did we learn earlier? That this is the probability of A plus the probability of B. 0.2 plus 0.4, 0.6. Find the probability of A but not, so A and, which is intersection, not B, B dash. How are we going to find that probability? Now, when in doubt, draw it out. Okay, so if you were to draw a quick Venn diagram, you're going to have your A, your B. They're mutually exclusive. Okay, so this is 0.2, 0.4. What do probabilities add up to? 1. So there's 0.4 on the outside. So where is A? A is here. A intersection, not B. Not B is on the outside. Okay? So that means the answer is just 0.2. Then it says the probability of neither A nor B. So it's A not and B not. A not and B not is the outside essentially, isn't it? 0.4. So events A and B are independent. Okay, now if events A and B are independent, we did learn a rule. Okay, A and B is the probability of A intersection B equals the probability of A multiplied by the probability of B. So therefore, to find the probability of A and B, which we know means A intersection B, we're going to do 1 over 3 times 1 over 5, which equals 1 over 15. You need to know this rule. And you need to know that and means intersection. Next question. The Venn diagram shows the number of key students in a particular class who watch any of 3 popular TV programs. Find the probability that a student chosen at random watches B or C or both. Find the probability that a student watches B or C or both. So, or means union. So we actually want the probability of B union C, which is the probability of B plus the probability of C. 4 plus 5 plus 10 plus 7 is 26 out of a total 4 30. So there's 30 people altogether. It then says, determine whether watching A and watching B are statistically independent. Okay, what do we know about independent? We know the probability of A intersection B equals the probability of A multiplied by the probability of B. This is for independent events. So, if we're determining whether they are independent, A and B, if they're independent, the probability of A intersection B will equal the probability of A multiplied by the probability of B. Probability of A intersection B, we know, is 4 out of 30. This should equal the probability of A, which is 7 out of 30, multiplied the probability of B, which is 19 out of 30. Okay? So that means that 4 over 30 should equal 7 times 19, 133, 30 times 30, 900. Do they equal each other? Absolutely not. Okay? Therefore, not independent. Okay, test your understanding. Some similar questions here. Off you go. Okay, so there are 3 events, A, B and C. The events are mutually exclusive, A and B. So that means A and B don't touch. So to draw a Venn diagram, you could draw 3 circles. You're going to have A and B. They're mutually exclusive, and C's in the middle. Then it says the probability of A is 0.1. So this whole of A is 0.1. Then it says the probability of B is 0.6. So this whole area here, I'm going to use a different colour, everyone. This whole of B is 0.6. Okay? Determine the probability of neither A nor B. So this is essentially the probability of A dash intersection B dash, not A, not B. Okay? Now, if you think about it, not A is here, here, and here. Not B, here, here, and here. The intersection means where do they intersect? Where have I put 2 dots? Yeah? Now they intersect in that remainder of C and the universal set. Now for us, we don't know what the remainder of C or the universal set is, but we do know that within this, the probability will add to 1. So this is going to equal 1 minus the probability of A minus the probability of B, which is 1 minus 0.1 minus 0.6, which we know is 0.3. Okay? Question 2. The Venn diagram shows the number of people who like each of 2 different colours. Determine if A and B are independent. Now, if A and B are independent, we know the probability of A and B equals the probability of A multiplied by the probability of B. This is the rule for independence. So first of all, let's work out the probabilities. So it's out of 15 in total. The probability of A intersection B is 4 out of 15. There it is. So this is 4 out of 15 should equal the probability of A, 10 out of 15, multiplied by the probability of B, which is 9 out of 15. So 4 over 15 should equal 90 over 225. Now, if we were to simplify 90 over 225, we're going to get 6 over 15. 4 over 15 does not equal 6 over 15. Therefore, these events are not independent. next question. The Venn diagram shows the probability of each event. Given that A and B are independent. Okay, they are independent. If they're independent, what does that mean? That means the probability of A intersection B equals the probability of A multiplied by the probability of B. In the question, it's told you they are independent. So this means that this rule holds. It's true. So what is the probability of A intersection B? Okay? It is X. Now, because these are in decimals here, it's already in probabilities. This question here was in frequencies, but this is in probabilities, okay? So, we're going to get X equals, what is the probability of A? All of A is this. What is this? X plus 0.3. We're going to multiply that by the probability of B. B is 0.2 plus X. Okay, what we're going to have is we're going to multiply this out. We're going to see we've actually got a quadratic equation. Yeah? So if you think about this, we're going to have X equals X squared plus 0.5X plus 0.06. Okay, I've just multiplied out the brackets. So that means X squared minus 0.5X plus 0.06 equals 0. And what have I done here? I've just minused X. If I now put that into my calculator, I'm going to get two answers for X. I'm going to get X equals 0.2 or X equals 0.3. You could even factorize that if you want. So if you think about it, you're going to have X minus 0.2 and X minus 0.3 equals 0. So here are two solutions. So possible values of X for this to be independent is X is either 0.2 or X is either 0.3. Okay? And that would make whatever this is independent. Quick recap if we're using sets for sample spaces and events, okay? What we have here is rolling an even number, rolling a prime number, and then we can say, right, well, there's 3 chances out of a total 6, okay? We should all be happy with filling in a frequency diagram like this, where sometimes we don't have the totals, we actually write the elements. So, when we are combining sets and events, we're now going to discuss what the context of this means, and then we're going to discuss how we would write this in terms of our probability, you know, P of, and then we'd write down the set is going to equal. Here we go. So combining sets and events, the context. What does this mean? Not A. Okay, so we know it means not A, but what's the context of the question then? What does that actually mean? What does not A mean? For the context of the question, this would be, because A is rolling even numbers, so the context of the question, not A, would be rolling odd numbers. Okay? Rolling odd or not rolling even. Think about the context of the question. So, this is just the probability of A dash, which we know, where is not A? Not A is here and here. So this is a total of 1, 2, 3 out of a possible 6, which is a half. So then for the second question, I'm just going to take this away. It wants the probability of A union B, which means A or B. And this is the probability of rolling even or prime in the context. Now, what is the probability of... So, the formula that we know, probability of A union B equals the probability of A plus the probability of B, is only valid if they're mutually exclusive. This is not mutually exclusive, okay? We can see by the Venn diagram they're not separated. They have something in common. So what we need to do is the probability of A union B, if we have a look, A union B is everything, everything in A plus everything in B. So the union is where they're, or it doesn't matter if the dots are shared or not. 1, 2, 3, 4, 5 out of 6. Okay, now the intersection means A and B. The context of this means we want an even prime number. And we know there's only one even prime number in the whole world. And it's 2, which is 1 out of 6. And remember, when we're looking for the intersection, if you are colouring in your A's and your B's, we're looking at where they cross. Where do they both intersect? They both intersect in this section of this Venn diagram, okay? Okay, the next one, we have A intersection B dash. Okay, A intersection B dash. This means rolling an even number which is not prime. Okay? An even number and it's not prime. So how I like to do these types of questions is A, I colour in where is A. B dash, where is not B? Here and here. Then it says intersection. Now intersection means where they have the two, where do they intersect? Where have I put them both dots in? And it's in this section here, which is only 4 and 6. So that means the probability is 2 out of 6, which is the same as a third. Now for the next one, it says A union B complement. So this means what is the probability of rolling a number which is not even or a prime? Okay, now we know this, but if I was to do this, I'd do the probability of A, which is here. I'd look at where B is, which is here. The union is all of this. And then it says not. So that means actually we want the outside. So 1 out of 6. Remember, because this is typically saying not prime or even. Then the last one. Now again, I really like to visualise these using colours. So A is here and here. B, here and here. Intersection, the intersection of A and B is here. So now I've done A intersection B. Okay? And then it says not this. So it's everything else. It's this part, and this part, which is 5 out of 6. Now, there is a fun fact, okay? So this is saying not even and prime, okay? Now then, can you write down what this represents? So this is A intersection B. It doesn't matter about C, because if you think of just A and B on its own, this is where they intersect. So it really doesn't, we don't have to think about the C here. This is literally saying, think about A and B as two whole things. They intersect there. So this is A intersection B. Here we go. Next question. So this is A union B. Again, we do not need to worry about C yet, because this is just the whole of A becoming united with the whole of B. Okay, how about this question here? So they all intersect, so it's A and B and C, which is A intersection B intersection C. Okay, how about this one here? This is A intersection C dash, not C, because this is the whole of A and not C. So if you say it as words, and then you can change it into the symbols. Okay, next question. This is A and B and not C. So we're going to have A intersection B intersection C dash. Okay, last. Oh no, it's not the last question. So this is not A intersection, not B intersection, not C. Or this could be A or B or C, not. Fun fact, everyone. So, when you have brackets, A union B union C, not. If you were essentially to expand this bracket, this would be A not the union, which is the intersection, B not the union intersection, C not. Can you see? So that's why they're exactly the same. Okay then, how about this question? What is it? It's A not A, which is A dash. What do we have here? We have A intersection B intersection C not. Because this is A minus the intersection of B and C, isn't it? Okay, here we go. What do we have here? We definitely have A intersection, not B, intersection, not C. As we know, a Venn diagram can either contain specific outcomes of each set, the number of items in each set, for example, the frequencies, or the probability of being in that set. Now, what you need to be able to do is, no matter what you do, you can either change them into probabilities or frequencies, whatever's easier for you. For this question, a card is selected at random from a pack of 52 playing cards. Let A be the event that the card is an ace, and D be the event that the card is a diamond. Okay, well, first of all, what do we know about a pack of cards? So, A, D. Now, A is aces. How many aces are in a pack of cards? 4. D is diamonds. How many diamonds are in a pack of cards? 13. That's because there's 4 suits in a pack of cards. 52 decks, 52 in a deck. 52 divided by 4, 13. How many aces are diamonds? 1. So I know that's going to go in the middle. Then, if there's 4 aces in total, that means that 3 aces are not diamonds. If there's 13 diamonds, 12 are not. And then this is going to give me a total of 16. There's 52 in a deck, so 36 must be on the outside. That is not in our... This is the worst rectangle I've ever drawn. Okay then, so 36, will be the rest. So then, this wants us to find the probability. So if you did want to, you could have drawn your diagram, and this is 1 out of 52, 3 out of 52, 12 out of 52, and 36 out of 52, okay? But you don't have to. Either way, if it says draw this using frequencies, please draw it using frequencies. Now, so A, N, D. Now again, I have to do this. So for each one, for this example, I'm going to draw a few for each example so that we've always got them here. I have to use highlighters, so I need to know what's going on. Okay, for the first one, I've got A. So my A is these two. And then I've got D, which is here and here. Intersection, where do they intersect? So I actually want this part in the middle. This is 1 out of, probability of A intersection D is 1 out of 52. Okay, the next one, probability of A is there and there. Probability of D, here and here. It wants the union, so anywhere where I've just put dots. So it wants this whole one here. So this is the probability of A union B, so D, A or D, which is 16 out of 52, because I'm going to add them all up. Okay, next one, probability of not A. So if I colour this in, not A, I'm going to do in yellow. So that's not A and that's not A. So that means not A is this section here. Everything that's not A. If you think A is that white one, this is not A. Probability of A dash is 48. 12 plus 36? No. Yep, 48 out of 52. Then the last one says probability of not A intersection D. So not A, I know, is, so not A is here and here. D, we know, is here and here. Intersection means where do they both cross? They were both only in this area here, weren't they? So that means the probability of A dash intersection D is 12 out of 52. Given that the probability of A equals 0.3 and the probability of B equals 0.4 and the probability of A intersection B equals 0.25, explain why events A and B are not independent. Okay, now we know if A and B are independent, that means the probability of A intersection B will equal the probability of A multiplied by the probability of B. It's given us all of these three, and we can clearly see that 0.25 does not equal 0.3 times 0.4. Why? Because 0.25 does not equal 0.12. It then says, given also that the probability of C equals 0.2, that events A and C are mutually exclusive. So that means A and C do not intersect in any way, shape or form. Okay? And that events B and C are independent. So if B and C are independent, that means that they will cross. So our Venn diagram, when it says draw a Venn diagram, is going to look like this. Okay, now we know that A and C are mutually exclusive, so it goes A, C, B. Now we have to fill this in. Okay, so here's my Venn diagram. Step 1, draw your circles like this. Please make sure your circles look better than mine. Okay, that's our first step. Okay, so here we go. It has already told us that the intersection of A and B, which we know is this bit, is 0.25. So I'm going to work there, 0.25. It's then told us that the probability of A is 0.3. So the whole of A is 0.3. If I've already got 0.25 here, what's left over? 0.05. It's told us the probability of C is 0.2, okay? The whole of C is 0.2. So all of this is 0.2, okay? Now it's told us, and we know all of B is 0.4, but if we've already got 0.25, that means 0.4 take away 0, so this bit is 0.15. Everyone happy with that? But how do we find the intersection? It's told us they are independent. So we know the probability of B intersection C, because they are independent, is the probability of B multiplied by the probability of C. Now here, when we're finding the probability of the B, it's the whole one, isn't it? So this is 0.4 times 0.2, which equals 0.08. So that means that my intersection is 0.08. Now we know that the whole of B is 0.4, so if I've got 0.25 and 0.08, what's left? 0.07. And we know that C is 0.2. If I've got 0.08, this one C is 0.12. Okay? The whole of the probability should add to 1. So when I add all these up, I get 0.57. So that means on the outside it's 0.43. So then, it says find the probability of A intersection B dash union C. Now I'm going to show you this, how to do this 2 different ways. Okay? So, first of all, we know that intersection means and. Do you remember in GCSE whenever we did and, what did that actually mean? We were doing multiplying, didn't it? And we know that union equals or. And if we were saying or, what did we have to do? Add. Okay, so we can use this. I'm going to show you 2 different ways to answer this question. Way 1. Okay? You have your Venn diagram. A, B, C. Actually, I'm going to draw it here. A, B, C. Okay, and we start by using highlighters. Okay, let's think about this. Where is A? Here and here. Where is not B? Here and here and here. And then it says intersection. So this is the whole intersection. This is where they both cross. So this is this section here. Is everyone happy with that? So this whole bit now, actually, is now this green bit. Then C. C is here and here. Okay, and it says union. So it just means wherever I've coloured in the green and the whole of C. So this is in fact the whole of the green. We just know from here is 0.05 plus the whole of C, now we know is 0.2. So that means the answer is 0.25, okay? So I've done that by colouring in and figuring out what's what. When you break this up, okay, you can do it. So first of all, find the probability of A intersection B dash. Once you find that probability, you know then that you want to find the probability of that union C, which means whatever your first answer is, you're going to add C on, the probability of C. Okay? Personally though, this method is good, all right? Okay, test your understanding. Here is a typical exam question, 3 marks. So the Venn diagram, figure 1, shows 3 events, A, B and C, and the probabilities associated with each region of B. The constants P, Q and R each represent probabilities associated with the 3 separate regions outside B. The events A and B are independent. Okay, if A and B are independent, that means the probability of A intersection B equals the probability of A multiplied by the probability of B. A intersection B is 0.1. Okay? Equals the probability of A. A is this whole area here. So this is P plus 0.1 multiplied by the probability of B. Now we know B is all of this in here. So B is 0.4. So now I'm going to multiply this out. 0.1 equals 0.4p plus 0.04. So then we're going to get 0.06 equals 0.4p. Divide both sides by 0.4. P equals 0.15. So there we've worked out. Easy 3 marks. Tree diagrams. We have done this at GCSE. 3 yellow counters and 2 green counters in a bag. I take 2 counters at random. Determine the probability that they are of the same colour. Now, if she takes 2 counters, that means she's taken 1, she doesn't replace 1. So when you're drawing your tree diagram, okay, and you have your yellow and your green, then you're going to have yellow or green, aren't you? If you think about it, the total of yellow are 3 out of 5. So the total of green are 2 out of 5. If you've already taken a yellow, we're now out of 4. Okay, so this is 2 out of 4, 2 out of 4. If then you take a green, you're still going to have the same amount of yellows as you started, but then you're going to have 1 out of 4. Everyone should be completely happy with this from GCSE. If you're not, you need to go back and learn some prior knowledge. So the same colour means we're going to have the probability of yellow, yellow, or the probability of green, green. Okay? So we're going to have 3 over 5 multiplied by 2 over 4 plus 2 over 5 multiplied by 1 over 4, which is 8 over 20. Part B. They are of different colours, so that's the probability of yellow-green plus the probability of green-yellow. So we're going to have 3 over 5 times 2 over 4 plus 2 over 5 times 3 over 4, 12 over 20. Now, I could have figured that out a completely different way as well. I could have just done 1 minus the probability of yellow, yellow minus the probability of green, green. Because if they're different colours, that's the opposite to them being the same colours, okay? So it's being able to spot that. Okay. Then here we go. The probability I hit a target on each shot is 0.3. I keep firing until I hit the target. Determine the probability I hit the target on the 5th shot. So how many times did you fail? 4. So remember, this is the probability of failing and failing and failing and failing and hitting the target, winning. Okay? So this is, the probability of failing is 0.7. But it's fail, 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 fail. So 0.7 times 0.7 times 0.7 times 0.7 is the same as writing 0.7 to the power of 4, multiplied by 0.3 to the power of 1. Now what you notice here is if he hits on the 5th shot, what do our powers add up to? 5, okay? We're going to come into that in a bit more detail later. So this is the same as 0.07203. So, conditional probability. This is something that's a little bit new, but isn't. Okay? Because this is given that. So earlier we looked at the Venn diagrams, what would happen. And you know, we did that earlier on. I think it was yesterday. We did really well. So, if this is the probability of A, then this is the probability of B given A. Okay, and this is how we write given, this straight line. Remember, mathematicians are lazy. We're not going to write G-I-V-E-N. Okay? So, the probability of B given A, we can use a formula. It's the probability of A intersection B over the probability of A. Now, what you find is whatever it's given by is always the denominator. So if it's find the probability given C, our denominator is the probability of C. And then if it's B given A, it's the intersection of them both, okay? Now, we know the probability of A intersection B, if these, we can get by doing the probability of A multiplied by the probability of B given A. And this is where this formula comes from. Okay? This is the formula you need to know. So, here are some examples. The following two-way table shows what foreign language students in Year 9 study. B is the event that the student is a boy. F is the event they choose French as their language. Determine the probability of F given not B. So we could use the formula. And to use the formula, we know the probability of F given not B is the probability of F intersection not B over the probability of not B. So this is what if we're using the formula, yeah? The probability of not B is 60 out of 100. Okay? Because the total of not B is 60 out of 100, yeah? Or we could have written 0.6 if we wanted. The probability of, I keep wanting to say female, but it's not, French intersection not boy. So French and not boy is 38 out of 100. So then my final answer is 38 out of 60. Okay? Now, there is another method we could do. The other method is just by looking at what's going on instead of not using the formula. We're finding the probability of F given not B. So what is the total of not B? 60. We're only going to focus on this column, not B, because this is given. So the total is 60. This is not B. And then, how many have chosen F in not B? 38. So you can see we can either use the formula or we can just use common sense. Okay? So for part B, it says the probability of B given not F. So the total of not F is 48. How many chose B out of not F? 22. Oh no, sorry. It's B, 26. 26 out of 48. Or again, you could use a formula. You can apply the same method to this Venn diagram right here. Method 1, using the formula. Probability of A given B is the probability of A intersection B over the probability of B. The probability of A intersection B is 2 out of 15. The probability of B is 6 out of 15, which is going to simplify to 2 over 6, which is 1 over 3. Or, to find the probability of A given B using just looking, it's the probability of choosing A given B. How many are in B? 6. 2 plus 4 is... And what is the probability of choosing A from this section only? Actually, there's 2. 2 ways. So we've got 2 more questions. So then, for the next 2, you can either use the formula, or you can just have a look. The probability of not A given not B. Well, not B is everything that's not highlighted here. So that's out of 9, isn't it? Okay. And what's the probability of choosing not A out of 9? Well, not A is only the actual outside. So it's 3. Now, if you're not sure how to get this, please use the formula. Then the next one is the probability of B given A union B. Now, A union B is this circle and this circle. So 6 plus 2 plus 4, which is 12. And the probability of choosing B from this is 2 and 4, which is 6 out of 12. Now, again, if you're not happy with this, please use the formula. Right, take a second and give these a go. Okay, so the first question, it says, given that the probability of A equals 0.5 and the probability of A intersection B equals 0.3, what is the probability of B given A? Well, we know the formula is the probability of A intersection B over the probability of A. So actually, this is just going to be 0.3 divided by 0.5, which is 0.6. For part B, it says, given that the probability of y equals 0.6 and the probability of x intersection y equals 0.4, what is the probability of not x given y? So again, drawing a Venn diagram may help. I always think when in doubt, draw it out anyway. So you can draw your x and y. You know that intersection is 0.4. You know that y is 0.6, so this is 0.2. Okay? So the probability of not x is going to be given y. So if you think, right, I always start this side. Y is here. Not x is this section out of that bit. So the answer is 0.2 out of 0.6, which is going to equal a third. I would never write 0.3 recurring, okay? If it is a recurring number, leave it as a fraction instead of a decimal. Part C. The probability of A is 0.5, the probability of B is 0.5, and the probability of A intersection B is 0.4. What is the probability of B given not A? Again, I'm going to draw this out. Now, A, B, it's given as the intersection, so we know that's 0.4. We know A is 0.5, so this must be 0.1. We know B is 0.5, so this must be 0.1. 0.1 plus 0.4 plus 0.1 is 0.6. So that means on the outside I have 0.4. So what's the probability of B given not A? So first of all, where is not A? I'm going to colour that in yellow. Not A is on the outside and this part of B here. So not A has a total of 0.5. We know that's my denominator. Over the probability of B. Now this is B given that, so I can only choose B given what I've already highlighted. Everything else is rubbish. Where is B from what I've highlighted? It is only in this section here. So this is 0.1 over 0.5, which is 0.2. Quick check your understanding. You have, please draw a Venn diagram, and I will go through the answers in a moment. So some tips. Let's really think about what's going on here. The probability of E is just this whole circle here. Everyone should be happy with that. The probability of E union F is E or F. The probability of E intersection not F. Now, I'm just going to break this up. E is here. Not F is here. And the intersection, where do they both cross, it's here, just this little section here. So now you've got all this information, you are able to fill out your diagram. So you know that this section here is 0.11. But you know the whole of E is 0.28, so you're now able to work out this one, which is 0.17. You know the union, which is this, this, and this, adds to 0.76. So that means you need to do 0.11 plus 0.17 minus 0.76. What do we get? 0.48. We also know probabilities have to add to 1, so if we add them all up and do 1 minus 0.24. So now I've drawn my Venn diagram, I can see what's going on. So question 1 says the probability of E intersection F. We know it's this part here, which is 0.17. The next probability just wants F. We know the probability of F is this whole circle here. If we add them together, we're going to get 0.65. Now, this says the probability of not E given not F. So you can either use the formula or you can draw it out. So first of all, not F. Where is not F? I'm going to use a completely different colour. Not F I'm going to do in pink. Not F is the outside and this part here. It's basically 1 minus what I've just got. This is not F. Okay? The probability of not F is my denominator, which is 0.35. Okay. Now it wants the probability of not E given not F. Well, where else is not E? Only from the pink part I've shaded. This part. So this is 0.24 over 0.35, which is going to give me 24 over 35. Okay? Or you could have used the formula. You could have used the probability of E dash intersection F dash over the probability of F dash. So, some extra practice here. Now, just to confirm the rules that we know the probability of A given B equals the probability of A intersection B out of the probability of B. The probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. Okay, and this is a generalized form. If A and B are independent, we then know the probability of A intersection B equals the probability of A multiplied by the probability of B. And the probability of A given B equals the probability of A. If A and B are mutually exclusive, okay, we know the probability of A intersection B equals 0, and the probability of A union B equals the probability of A plus the probability of B. But in general, okay, we can use these rules here. Now, we've already seen this first rule that I've highlighted in pink. And this second rule, we are able to prove, and we're going to do that a little bit later, okay, using a Venn diagram. Okay, when in doubt, draw it out. It's the only way to, if you're not sure, give it a draw, okay? So, the probability of A intersection not B. So first of all, my A is pink. My not B, blue. Intersection means where do they both cross? It's in this section. So the probability of this is 0.4. So I know this is 0.4. For the next one, my probability of A in pink. My probability of B, I'll do in green. Not green, actually, we've just used green. Dark pink. No, that'll just make life complicated. Yellow. Okay, and B's in yellow. And it's the union. So, let's get a different colour all entirely now. Grey. And the union means wherever I've done it. So it means the whole thing, all of it, is 0.75. So the probability of B, it stands to reason, the probability of A union B minus the probability of A intersection B dash is going to be 0.35. Because if all of this is 0.75, if I take away this part here, all I'm left with is the whole of B. It then says, what is the probability of A dash intersection B dash? Okay, so, A dash independent intersection B dash. Now, if we know the whole of this is 0.25, the outside is 0.25, isn't it? Probabilities add up to 1. Now, the intersection of not A and not B is this whole area. So it's 1 minus 0.75, which is 0.25. It now says the probability of A is 0.47, and A intersection B is 0.12, and the probability of not A intersection not B is 0.03. Then, what is the probability of A given B dash? Okay, to find the A given B dash, I know the formula I'm going to use. It's the probability of A intersection B dash over the probability of B dash. Now, have I been given A intersection B dash? No. Have I been given the probability of B dash? No. So I need to find these probabilities, don't I? So what I can do is I can either see if any formulas will help us or work them out. But I think it'll be quite easy. So 0.03 is on the outside. Probability of A is 0.47. So this must be 0.12. Take away 47 is 0.35. And then what's remaining should add up to 0.97, shouldn't it? So what's the answer? 0.5 should be, is that right? So the probability of B is 0.62. So now we're able to find out what's going on. The probability of A intersection not B. So my A is going to be pink. Probability of A is here and here. Probability of B dash, here and here. Where do they intersect? Only at 0.35. This is over the probability of B dash. Well, if the probability of B is 0.62, probability of not B is 0.38, or in other words, all the blue bits added up together, because that's not B, isn't it? Okay, when I put that into my calculator, I don't know what it is, but what I do know is this is equivalent to 35 over 38. I'm not going to leave it as a decimal on a fraction, okay? Then, question 3. Probability of A dash equals 0.7. I don't know if I need a Venn diagram, but it's always good to have one ready. Not B is 0.2. A intersection not B. So where is A intersection not B? A is here and here. Not B is here and here. The intersection is 0.1. So where do they intersect? They intersect here, which is 0.1. Okay? The probability of not A is 0.7. So that must mean that this and this is 0.7. So these two must add to 0.3. So this, the intersection is 0.2. Also, the probability of not B is 0.2, 0.1, and the outside must equal 0.2. And they all need to add to 1, so this must be 0.5. So I've figured this all out. And what it wants is the probability of A union B dash. Now, I can use that first formula. The probability of A plus the probability of B dash minus the probability of A intersection B dash. Now, the probability of A, 0.3, plus the probability of B dash, 0.2, minus, and they actually tell us this, 0.1. Okay, this is going to give me a total of 0.4. We didn't even need to draw the Venn diagram for this. And just so you know, the probability of A is 1 minus the probability of not A. Sorry, made a slight error. So, oops. Yeah, so the probability okay. So the probability is 0.1 because the probability of not B, which is here and here. So that means the probability of B, this is 0.6. Yeah, sorry, that makes sense because not B is 0.2. So B must be 0.8. And 0.2 plus 0.6 equals 0.8. Now for the last one, we know this is going to give me the probability of B intersection A dash over the probability of A dash. B intersection A dash. Let's do that. Probability of B is now pink. Probability of A dash, not A, here and here. Where do they intersect? 0.6 over the probability of not A, which is 0.7, which is 6 over 7. Okay, so here's a question for you to test your understanding. So from previously, we already worked out the probability of P is 0.15. Did we work out the probability of Q? 0.3. Okay, and it says given that the probability of B, given C. Now we know The probability of B given C means the probability of B intersection C divided by the probability of C. Okay? Now, the probability of C is the whole of C. Now, the whole of C is Q plus 0.2. The probability of B intersection C. So if B is pink and if C is blue, where is the intersection? This is 0.2. Now this tells you this equals 5 over 11. So from here we can cross multiply. So I'm going to get 11 lots of 0.2 equals 5 lots of Q plus 0.2. Expand, rearrange, and then I'm going to get Q equals 0.24. Then, how am I going to find R? Now we know R is the universal set on the outside. If I add all these probabilities up and do 1 minus, it's going to give me R. So 1 minus 0.15 plus 0.1 plus 0.1 plus 0.2 plus 0.24. If I add them all up, this is going to give me the probability of R, which equals 0.21. The last part says, find the probability of A union C given B. Okay, so how does this look? A union C given B. This looks like this. The probability of A union C given B. Using our formula, we know this is the probability of A union C intersection B over the probability of B. Okay, so A union C is what is your A union C? Okay, so A union C. First of all, A is going to be green. So this is A. C we know is blue. Okay, now the union is all of it. So here we go. It's here and here. This is A union C. Then B is pink. Then it's the intersection of A union C. Where do they intersect? They intersect here and here. So this is the total of 0.3 over the probability of B, which is 0.4, which equals 3 over 4. Okay, so the laws of probability, we already looked at them just a second ago, didn't we? Okay, make sure you keep that safe. Actually, which slide did we look at them on? 42. So go back to slide 42 for the laws of probability. So when we're answering these types of questions, first of all, A and B are both definitions that we need to learn. C, D and E are calculations, but for C, D and E, it tells us that A and B are independent. What do we know about independent events? Yeah, for independent events, the probability of A intersection B equals the probability of A multiplied by the probability of B. If you see independent, I want you to write this down. It's the set of all outcomes. The set of all outcomes. So it's a set of one or more outcomes and is a subset of the sample space. Okay. Part C. Now we know because they're independent, we just need to do the probability of A multiplied by the probability of B. So a third times a quarter is 1/12. Now, for part D, the probability of A given B. That means the probability of A given B is the probability of A intersection B over the probability of B. Now, because they are independent, probability of A intersection B, we know we can rewrite as the probability of A multiplied by the probability of B over the probability of B. So actually, they're going to cancel. And the probability of A given B is just, in fact, the probability of A. And the probability of A equals a third. Then the probability of A union B, we know the rule is the probability of A plus the probability of B minus the probability of A intersection B. So we're going to get a third plus a quarter minus a 12, which is going to give us 6/12, which is a half. Question 1. C and D are two events such that the probability of C is 0.2, the probability of D is 0.6, and the probability of C given D is 0.3. Now, we could draw a Venn diagram, and I do always say, when in doubt, draw it out. But we could also use the formulas. We know the probability of C given D is the probability of C intersection D over the probability of D. Now, we know the probability of C given D is 0.3 because it tells us in the question. So this equals the probability of C intersection D over the probability of D, which again tells us in the question. So that means the probability of C intersection D is 0.3 times 0.6, which is 0.18. Now it says find the probability of D given C. Now the probability of D given C is the same as the probability of C intersection D. We would write D intersection C, but that's the same. Over the probability of C, which is 0.18 over 0.2, which is 0.9. The next it wants the probability of C union D. Now, we know this is the probability of C union D equals the probability of C plus the probability of D minus the probability of C intersection D. Probability of C, 0.2 plus D, 0.6 minus the intersection, which we worked out in part A, 0.18, 0.62 is the final answer. Okay. Stating was the relationship between two events R and S when the probability of R intersection S is 0. If their intersection is 0, what do we know? Absolutely, they are mutually exclusive. Okay, so mutually exclusive. Okay, part B. If they are mutually exclusive, we know we can use anything but the addition rule. Now, the addition rule states the events A and B are independent, so we can use the addition rule. If If we want the probability of B, now if we think about what rules we've got this given rule, and we've got the addition rule, which is this one here. Oh, this one here. So the addition rule is the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. Okay? So, what do we know? We know the probability of A is a quarter. We know the probability of A union B is 2 over 3. So, step 1, substitute. 2 over 3 equals a quarter plus the probability of B minus. Now, what do I also know about the probability of A intersection B? Okay, well, it tells us these events are independent. So that means the probability, if they're independent, what is the rule? The rule is the probability of A intersection B equals the probability of A multiplied by the probability of B, doesn't it? So instead of writing the probability of A intersection AB, I'm now going to substitute this in. This is going to be a quarter times the probability of B. I'm now going to rearrange, simplify, okay? 2/3 minus a quarter, 5 over 12. Probability of B minus a quarter probability of B is 3/4 probability of B. Times by 4, 20 over 12 divided by 3. Is that right? Times by 4 is 20 over 12, isn't it? Divide that by 3. 5 over 9 equals the probability of B. Okay, so what we've had to do there is use two formulas, the addition rule, and then we know about independent events, okay? It then says, find the probability of A dash intersection B. So that means, because they're independent, this is the same as doing the probability of A dash times the probability of B. Now, A dash is 1 minus the probability of A, which is 3/4, and B, we just worked out, it's 5 over 9. Multiply them together, 15 over 36, which is 5 over 12. It then says, find the probability of B dash given A. So this is the probability of B dash intersection A over the probability of A. Now, the probability of B dash intersection A is the probability of not B times the probability of A all over the probability of A. So remember, we can cancel these out. So this is the same as writing just the probability of B dash, which is 1 minus the probability of B, which is 4 over 9. Right, everyone, test your understanding. Off you go. So, 3 events A, B, and C are defined in the sample space S. The events A and B are mutually exclusive. That means that A intersection B equals 0. They're mutually exclusive. They don't even interact. A and C are independent. So that means A intersection C equals the probability of A multiplied by the probability of C. This is what we get from here. Now, if we were to draw this, because A and B are independent, I would draw like this, and I would have A, C, B, okay, because A and B are independent. And this is how I would draw to illustrate it. Now, don't forget to draw a box around it and write the universal set. That's all you have to do. Part. Next bit. Given that the probability of A equals 0.2, the probability of B is 0.4, and the probability of A union C is 0.7, find the probability of A given C. Now, because A and C are independent, we know the probability of A given C is actually just the probability of A, which is 0.2. Why is that true? Because they're independent, probability of A given C is the same as the probability of A intersection C over the probability of C. When they're independent, the probability of A intersection C is the probability of A multiplied by the probability of C over the probability of C. The probability of C's are going to cancel. For part C, it wants the probability of A union B. Now, we know A and B are mutually exclusive, so the probability of A union B is given by the formula, the probability of A plus the probability of B. It tells us A is 0.2 and it tells us B is 0.4. When we add them together, we get 0.6. Again, if you don't know that rule, you need to write that down. Part D, it wants the probability of C. So what I'm going to do is I would probably use the addition formula, okay, with everything we have, because the probability of A union C equals the probability of A plus the probability of C minus the probability of A intersection C. Now, in the question, it's told us the probability of A union C is 0.7. So I'm going to write 0.7 here. Equals the probability of A, it told us in the question, 0.2. The probability of C is what we're trying to work out. And the probability of A intersection C, now we know A intersection C is the probability of A times C. So this is going to be 0.2 lots of the probability of C. So all I'm doing is manipulating the rule, writing in what the facts I know, and then rearranging. So I'm going to get 0.5 equals 0.8 lots of the probability of C. So therefore, the probability of C is going to equal 5/8. Okay, some super important tips. Now, Dr. Foster's done this, and he says if he was to identify 2 tips that will possibly help you in the most probability questions. So, if you see the words given that, write out the law immediately, okay? And for example, this is the probability of A given B equals the probability of A intersection B over the probability of B. Then, given that Bob walks to school, find the probability that he's not late. So given that means whatever is given, so walking. Not late is late dash. This is how we would write that. And we know this is the probability of L dash intersection W over the probability of W. The next one, if you see the words are independent, immediately write down the laws for independence. The laws for independence are the probability of A intersection B equals the probability of A multiplied by the probability of B. The other law, which we've seen at the minute, is the probability of A given B is just going to be the probability of A. And we can prove that law by using the one above, can't we? If they're independent. Okay, probability trees. So, the only difference with this and what we saw at GCSE is conditional probability. Okay? Now, for probability trees, you know, if you don't know the probability, you could just write probability, and then this would be 1 minus that probability, because you know probability on one branch adds up to 1. In this case, we know it. It says in the question, you've got 2 bags. Okay, so this is bag 1. This is bag 2. The first with 5 red balls and 5 blue balls. Okay, how many balls is that altogether? 10. And if this is red, this is 5. And if this is blue, this is 5. Okay. The second bag has 3 red and 6 blue. You pick one from the first bag and place it in the second bag. Oh. Right. But first of all, let's think about this. There's 3 red, so 3 out of 9, 6 out of 9. 3 out of 9, 6 out of 9. This is what's in bag 2, isn't it? But when we read the question, let's think about it. I always like to start at the beginning of our journey. Here we are. I've put my hand in the bag and I've picked a red ball. I'm now going to put it in this bag. If I now put it into this bag before I then pick a ball, how many balls are now in the bag? 10. Okay, this is a key point. These are all going to be out of 10 now. Now, I picked a red. So if there's 3 in the bag and I put another red in, how many is there? 4. Perfect. Now imagine I'm still here. I picked my red, but this time I put it in and I pick a blue. Does the blue change? No, we still have 6 blues. Perfect. Here, start at the beginning. I put my hand in the bag, I grab one, it's a blue one. Okay? I put it in the bag, and now I have the chance to get a red. Does my red change from 3? Absolutely not. Okay? If I go back to the beginning, I've got my blue one, and I put it in the bag. How many blues are now in the bag? 7. Absolutely. So now I filled this in, I can now have a look. The probability you pick a red ball on your second pick. The only way I can find a red ball on my second pick is red, red, or blue, red. Okay? So, the probability of picking a red on the second pick is actually the probability of red 1 intersection red 2 plus the probability of blue 1 intersection red 2. So we're going to get 5 over 10 times 4 over 10, which is 20 over 100, plus 5 over 10 times 3 over 10, which is 15 over 100, which is 0.35, or 7 over 20. Now, the last one says, given that, okay? So, given that your second pick was red. So that means my denominator is second pick red, which we know is 0.35. Okay? We need to find the probability of, given your second pick was red, the first pick was also red. So that's R1 intersection R2, which is 5 over 10 times 4 over 10, which we know, 20 over 100, I don't know why I put 200, sorry. 20 over 100 multiplied by 0.35, because we just want red, red, divided by 0.35, which gives me 4 over 7. So here's another example. On a randomly chosen day, the probability that Bill travels to school by car, by bicycle or on foot is a half, 1 over 6 and a third respectively. So we know we have to draw our probability tree like this. And then it goes on to say the probability of him being late is 1 over 5, 2/5. So you can see if he gets the car, then the probability of him being late is a fifth. So we have to draw each one corresponding. It says, given that Bill is late. So given that he is late, find the probability that he did not travel on foot. So we're finding the probability that he didn't travel on foot given he is late. So that's foot not given that he is late. Now we know this is the same as the probability of not on foot intersection the probability of being late over the probability of being late. So this is going to be probability of him not being on foot is 1/6 and then being late times 2/5 plus the probability of still not being on foot is a half multiplied by being late, which is 1/5. And then we're going to divide that by the total probability of being late, which we know is going to be a half times 1/5 plus a sixth times 2/5 plus a third times 1/10. I'm going to put that all into my calculator and my answer is 5/6. Alternatively, I could have just done 1 minus the probability that he is on foot given that he is late. Okay, now I want you to pause the video here and give this question a go. Okay, and here is the mark scheme for this question. Please check that you've tested your understanding correctly and you understand what's going on. Well done, everyone.